Morning, everybody. I'm Jing Chen from Algorand. Let me tell you something about our project. And I'm also from Stony Brook University, and right now I'm taking a leave to work full-time on our project. So, Algorand at its core is a distributed public ledger. It is scalable, it is secure, it is decentralized, all at once. And we developed our protocol from first principles with provable worst-case guarantees rather than heuristics. And Algorand is very flexible and enables continuous evolution in the system, whether it is a tech level or policy level. So what is a decentralized distributed public ledger? Well, a ledger, we all know what it means. A manager of a store tries to write down all the transactions in a store on a piece of paper according to the exact order the transactions happen, right? Now, a virtual ledger is a sequence of transactions organized in blocks. Pictorially, we chain up the block so that, the word blockchain, where it comes from. Mathematically, that means that a block will include the hash of the previous block as a part of it. So that's how we chain up things online, right? And what are the requirements for such a structure? A, it is readable by all. It is writable by all. It's tamper-proof for all. Now, when I say all, I don't just mean all in this room. I really mean all on the internet. So it's really large scale, a very challenging problem. And now, if you don't look at the last requirement, the first three can very well be achieved by a centralized database. But it is well understood that a centralized management would be easily corruptible, would be the bottleneck of the system, and so on and so forth. So what makes distributed public ledger stand out is that it achieves all those without a centralized management. So what is it good for? Well, it can give us notarization and provide storage. It can order chaotic data. It can provide a virtual trust party for contracts. It can help with settling payments and support cryptocurrencies. And it achieves all this without centralized management. Now, this is good. This is more than good. This is a dream infrastructure that many of us have felt so excited about. But however, the true question, of course, is how are we going to implement such infrastructure? Now, before I tell you the Algorand approach, let's just fly back in time and look at the Bitcoin, where everything began, right? Now, Bitcoin was the most exciting part about Bitcoin is really it is providing a consensus among a permissionless system. There's no bar about when you can enter. A user can control many keys. There's no identity associated with them. Everybody can participate and everybody can contribute. Really permissionless and decentralized. The main idea for Bitcoin is to achieve eventual consensus with proof of work. And the main assumption here is that the majority of computing power is controlled within honest hands. If this is violated, then blockchain could be subverted, transaction could be erased by adversary. However, what are the technical problems here if we look at it closely? Well, it is very wasteful and costs a lot of electricity to run, to mine blocks. Right? The recent number I heard is that Bitcoin is twice as much as Denmark. I think this number is still growing. And the fee for each transaction on average right now is like $7 per transaction. So I guess nobody is really paying Bitcoin for exchange a piece of pizza anymore. And what happens, an unintentional consequence of Bitcoin is exogenous concentration of power, which wasn't a part of the original design. Because mining is getting so challenging, right now we have about 4 major mining pools in the world. And this number has been shrinking in the past years. That is not really decentralized anymore. And when things have become centralized, then it causes exogenous vulnerability. Because the pools are known, there's low margin, it becomes easier to corrupt them. And And what about scalability? Today, we have about 10 million users in the whole Bitcoin system. And the system has already been very costly and pretty slow. What about 100 million users suddenly join the system tomorrow? Then the cost will be even much higher. And another thing is about ambiguity. We have been using the word blockchain all along. However, what is really happening is a block tree. At any moment in time, there are forks, there are branches of blocks that you need to wait for a long time for the block to be deep enough to solve the ambiguity there. And a consequence of forks is that you need to wait a long time to finally confirm a transaction. For example, you should wait at least for the transaction to be 3 steps deep, and that will be half an hour rather than 10 minutes. And right now, the recommendation is 6 deep. But however, if your transaction is really of high value and you want to be really sure, then you actually should wait even longer and can be hours or even days rather than minutes to confirm a transaction. OK. Now, I must say that the Bitcoin has been instrumental in our current ecosystem and has inspired many of us to rethink how to do distributed consensus. However, reflecting on this list, we realize that there are much more to be done here, and the torch has to be passed on to the next step. With this said, let me move on and tell you something about Algorand's approach. So in a nutshell, Algorand achieves consensus in a permissionless system. And the consensus is instantaneous rather than eventual. And the core technique is based on Byzantine agreements. Just to give you a little bit of idea, remember that the permissionless system really has many users, and each user can have arbitrary number of keys. And yet, each key is free to participate and may be given a chance to say, this is the next block, and the whole system will listen. What about instantaneous? Now, in contrast to mining, doing a lot of work throwing in mining blocks, so here we are really, I would like to picture Algorand's protocol as a feather, which is really weightless. And the blockchain in Algorand would pretty much evolve very fast, weightlessly. And there is no ambiguity, and there is no branch. So what happened to forks? What happened to proof of work? There's none of those. Algorand's chain, not only there's no hard fork, there's no soft fork either. So it is really a chain of blocks. OK, so finally about Byzantine agreement. This is a well-studied topic in distributed computation for many years. And on high level, this is a communication protocol that can allow users to reach consensus when the majority is honest. There wouldn't be much time for us to dig into the real concept, so I will just give you some picture that is really high-level story. So Byzantine agreement have 2 properties, agreement and consensus. What do we mean by agreement? There are a bunch of honest users. There are a bunch of malicious users. You can tell which is which by looking at the picture. So the honest users all have their own values in their mind. What would be the next block? What would be the next set of transactions? And after the communication protocol, everybody would output the same value, namely what would be the next block should be. It doesn't matter what the adversary can do here. And consistency is another requirement in addition, meaning that if all the honest users have already started with the same value, then the adversary cannot distract them to anything else, and they will agree on this value immediately. Those are the 2 components of Byzantine agreement. Now, at the first glance, it looks like this is exactly what we need and is enough to achieve consensus already. But what's the problem? The problem are the following. A, classic Byzantine agreements are typically very slow. Coming from computer science, we care about being polynomial time, being polynomial computation, communication, and so on. However, when it comes to billions of users and billions of transactions, polynomial guarantee is just not enough. So that's very slow. But a more serious problem here is that a Byzantine agreement works under a fixed set of users, where the identities are all known. And that is certainly not what we are looking for in a permissionless system. So how are we going to fix those challenges? Now that comes down to several techniques that we have developed in Algorand and we have implemented in our system. So the first key I want to share is our new super fast Byzantine agreement. And how fast it is? Well, it only requires one short message per participant per step. And even in the worst case, with adversary trying very hard to delay people, to cause confusion, the protocol will finish in 9 steps in expectation. What about good cases? Well, if we are optimistic about the adversary and we believe the system is in good hands, then it will only take 1 extra step after the block is propagated. And the protocol will reach agreement immediately. So it is really very fast. However, this is not enough. Why? Because it is still too slow to run if you have a billion users trying to exchange messages for this agreement. That will congest your network. What is our idea? Immediate idea is, how about you randomly and publicly select a small set of users, say 1,000, and let them run the Byzantine agreement and tell the remaining of the world what the next block should be. What is the problem here? The problem is that once this identity of those super users becomes public, the adversary can immediately corrupt them, twist their messages, or DDoS them to prevent them from reaching agreement. Therefore, if you use this approach, you need additional assumption. For example, it takes a day for an adversary to corrupt a user. And by the end of the day, whatever this user has said has already reached the consensus, therefore the corruption doesn't matter anymore. But we do not want to add this extra assumption. And I think it's a good time now for me to tell you what is the adversary model that we are looking at Algorand. Let me just read down the list for you. So the adversary can immediately corrupt any user he wants, up to a third. And the adversary has total control and can perfectly coordinate all the bad users, decide what messages they are going to send. Moreover, the adversary sees all the good messages first before he chooses bad messages. So he is adaptive. And also the adversary controls the delivery of good messages, except that in a propagation network, the messages are delivered within some bounded amount of time. For example, it is well understood that once a message is propagated, it takes about several seconds for it to reach maybe 95% of the user on the internet. The adversary has infinite computation power. Now that we cannot allow. The adversary cannot forge signatures. In other words, it cannot break crypto. Otherwise, there's nothing we can do here. If you look at this is really a very powerful adversary, adaptive corruption, full control, so on and so forth. And that is what we are trying to fight against in our protocol. Just another few words. What about the network? In our system, do we need centralized? Do we need synchronized clocks? Do we need almost synchronized clocks? The answer is no, we don't need any of those. What we need is that different users, their individual clocks, have the same speed. For example, my CPU and your CPU and somebody else's CPU in Europe or in China probably are not displaying the same time. But we can all count 1 second, 2 seconds, 3 seconds at the same speed. That's all we need. In other words, a minute is a minute for everybody. All right? So how are we going to fight against such an adversary? Well, the key is a technique we invented that is what we call cryptographic self-selection. Here the core is the word self. That is, each user secretly selects himself to participate in a Byzantine agreement. He has his own lottery to run, randomized, based on the history. And in this lottery, he cannot cheat. If he's not selected, he cannot fake up a winning ticket and convince others to accept his messages. But if he really wins this lottery, then he has a signature as his winning ticket that everybody is able to verify immediately. So with this approach, we can safely and secretly select a small set of users to participate in the Byzantine agreement. Because at this moment, every user is secretly selected, the adversary wouldn't know who to corrupt before seeing their messages. That gives the users a good level of protection. However, this is still not enough. What's the problem here? The problem is that the identity of a user will be revealed, or the IP will be revealed once the first message gets out. Then he's subject to corruption. And a user will be corrupted if he's put in charge for a long time. So our next idea to deal with this is a novel property of our agreement protocol that we call user replaceability. Pictorially, this is what we mean. Say the Byzantine agreement is running for several steps, step 1, step 2, 3, 4, etc. Now each step, a small set of users have been secretly self-selected to pass on the messages. I put different colors for the users. Why? Because I want to indicate that they are different users from different steps. Not only the identities are different, but because randomization is used, different steps may have different number of users. And what's important is that these users do not share any secret variable. There is no internal state being passed on. Every message is public. A user sends out one message, his job is done. The next user picks up the torch and come up with the next message, and he's done as well. So one message, one user, and even the adversary corrupts this user afterward, the message cannot be taken back. So that is what we call user replaceable, and that makes the system really, truly decentralized. All right, I'm still not done yet, because if we are running a permissionless system, having an honest majority of users doesn't mean much, because the adversary may very well control a majority of the public keys in the system. Who knows how many keys he has in his mind, right? So what is the trick? How do we go to a real permissionless system? And here our technology of choice is proof of stake. I'm sure a lot of you have heard of this term, but do we mean, say, delegated proof of stake, where a small set of users is selected to be in charge for a long time? Do we mean something like money in the middle proof of stake, where you have to put your stake on as hostage and cannot spend it, and your money may be confiscated if you are caught doing something wrongly? Or, there are many forms of hidden centralization in order to make the system work. Actually, we do not do any of those. And Algorand is really, truly decentralized. And we'd like to say it is the purest form of proof of stake. Your power in the system is proportional to the amount of money you have. You can spend your money anytime you want. You don't need to lock it up. And you don't need to delegate to anybody if you don't want to. So anybody, any stake is really free to participate and free to contribute. Okay, so far I have told you 4 technologies that we have used in Algorand. I must say that still, in order to make a really working system, more magic is needed in order for the system to work. And by magic, I mean mathematics here. So I'm not going to tell you all those details, and I believe they're available on the internet, and I welcome you to take a look at our papers and our implementation. So just to summarize a bit, the main idea in Algorand is a super fast and user replaceable Byzantine agreement. And we achieve permissionless system via proof of stake in a purest form. And the main assumption here is that the majority of money is controlled in honest hands. Well, do we believe this assumption holds? The only thing I can say is that if this assumption does not hold, then the world has more serious problem to deal with than how to build a blockchain. What are the technical advantages that we see? First of all, computation is really trivial. To run the protocol, you basically need to do some addition, some counting, some signing a signature, verifying signature, and so on and so forth. And it's really truly decentralized that you do not have many inputs versus small users really have only one class of users. There's no concentration of power. And also, because there is no fork, any transaction that enters the blockchain is immediately final. Well, when I say no fork, I mean the probability of fork is extremely small that can be ignored. For example, if the probability of fork is 10 to the minus 18, then you will, in expectation, need to wait the age of the universe to see a fork. And that's kind of the level of security we provide. And also, our protocol has a very good scalability. Basically, the overload to run the consensus protocol is very small compared with the transactions. And how fast the transaction can be cleared up really depends on the network, how fast they can be propagated in the network. And also, as I said, the adversary model we are thinking about is really very strong, so we are safe against a bad adversary. All right, just to put everything together, Algorand is a permissionless consensus infrastructure. It has no forks. There's no miners. There's no proof of work. The computation here is really trivial. It has perfect scalability. Whether the users is 10 million or 100 million, the real bottleneck is a network. And we have immediate transaction finality that you do not need to wait until the block to be, say, 1, 2 deep or 3 deep in order for it to be confirmed. And it provides provable security guarantee against a worst-case adversary. And what's more is that we are not sitting on our protocol and doing nothing, and we're continuing contributing to this system, and we have many new ideas that have been developed and are on the way to be revealed to the public. For example, our new protocol is secure against arbitrary network partition. This we are really considering like state-wide or nation-wide attacks. Somebody is willing to spend multiple $1 million, maybe separate Europe from US for a week, something like that. A very strong network partition, and yet Algorand blockchain still doesn't fork. And it will resolve shortly after the partition disappears. And as we said at the beginning, the protocol is very flexible so that in the future, if we want to change the governance policy, to change the block structure, then we can securely do that without causing hard forks. And we also acknowledge the importance of having a proper incentive structure in a financial instrument. And we provide secure incentives to the system. And also, I believe if you look at our website, you will notice some commitment in the form of hashed, several hashes committed to our website as indicator that we are continuing developing new technology that will be reviewed gradually when time comes. All right, so I have told you the core of Algorand, which is a distributed public ledger. Now, in terms of business development, we see our product as a first priority, go-to-market is a digital currency that is big for the globe. And in the long term, our vision would be to build Algorand as a truly decentralized consensus infrastructure that allows others to build applications based on our system. So there's a short-term goal, and there is a long-term goal. And in our structure, we really want to be scalable, to be secure, and to be decentralized. And with this said, our team right now is working very hard to build the system, to have everything done right. And we are growing. And we really look forward for you to join our journey. With that said, thank you very much.